have another hike. Last one. Sadly, this really truly is the last one. How awesome is it that it's called the Goat Trail? But I don't think it's the greatest one. I don't think it's the greatest of all semester. But I do think it's a good one. So this is another one in the Buffalo River area. So obviously you can see the Buffalo River down below in this picture. And if you don't like ledges or being high up, probably don't hike this trail. You have to hike through some like forest that's pretty cleared out. So you're not hiking on like a ledge the whole time. But the fun part of the trail is you do get to this ledge. It's just a very narrow path on a ledge. Keegan, you've been on this one a lot, huh? So some of you may have hiked it, but it's awesome. I don't know. Okay, the story of why it's called the Goat Trail. They say kids back in the day, it must have been a long, long time ago, used to like walk this trail to school with their little goats. And I just don't know how I feel about that because I would never let my child walk by themselves on this wide, like right here. This is where, and look, they could fall so easy. So I don't know how I feel about that, but that's what I was told. So I'm just passing it along. Maybe it's a conspiracy theory or a big fat lie. But yep, you can see the river. It's really, really pretty, especially in the fall. If you're floating the Buffalo River, different portions, you can see this trail. You just have to know which bluff to look for. But anyways, there's the Goat Trail. If you're in the Buffalo River area, it's a good one to hike. Recommend it. Okay. Chapter 1. So this is a very informal thing. Just like any other review, if I'm going too fast, stop me, slow me down. But I'm just going to hit the high points. So this is not like an all encompassing, but it is a review of the major topics from each chapter. Okay. And here's what I told this morning. There's going to be some of this that you're like, I remember that and I feel confident on that. And if so, I don't recommend you spend all your time practicing those topics as you prepare for final. You have limited time. Some of you have jobs and families and other stuff going on. Some of you are trying to move off campus or whatever. So with the time you have, focus it on the places that you feel less confident in. So if I go over something today that you're like, I just don't know that I fully remember or understand, put a star by that or make a note to yourself. You need to focus on that and go over those things for the final. You may not need to review all of this stuff, but here we go. Chapter 1, we talked about matter and we learned how to classify it. So we looked at the fact that there are things called elements and compounds. Okay, these are pure substances. Elements cannot be broken down any further. Okay, it's as simple as it gets. Compounds can be multiple elements, okay, put together. So you can break a compound down into its elements, all right? But it is still a pure substance in the sense of like water is a compound, 2 elements there, hydrogen, oxygen. You could break it apart into its elements, but pure water is just one molecule. It's H2O, one type of molecule present in the compound, okay? So those are pure substances. Then you have homogeneous and heterogeneous mixtures. Okay, how are these the same? They're the same in that they're both mixtures. Okay, a mixture contains multiple, I'll use the word ingredients or multiple compounds. Multiple things present in a mixture. How are they different? Well, a homogeneous mixture is uniform throughout. I don't think I spelled it. Okay, uniform throughout. So all of the ingredients, all of the compounds or the things are evenly mixed. Okay, heterogeneous is not evenly mixed. Okay. All right. So every portion of homogeneous mixture is the same, but not so for a heterogeneous mixture. So if I give you examples of different things, should be able to classify those as an element, compound, homogeneous, or heterogeneous mixture. Even if I gave you a small like picture diagram, you should be able to classify it. So that's classifying matter. 4 signs of a chemical change is something else we went over in chapter 1. So these are in no particular order: temperature change. And I want to make a point here. When you think of processes like freezing, melting, evaporating, temperature changes are involved, but these are not chemical changes. They're physical changes, because before and after the melting or whatever the process is, you have the same substance, right? A chemical change is where a temperature change involves changing the content, like the matter. Okay, so roasting, toasting, cooking, something like that. That is obviously a temperature change will be present, and it's altering the chemical substance. Second one would be a color change. Third one would be if we get gas bubbles. Okay. Anything bubbling is forming a gas. We made a new substance. And the fourth one would be formation of a precipitate. All right, so remember those. If I were to give you a simple process, scrambling an egg, or I don't know, roasting a marshmallow, or bleaching your hair, or something like that, you should be able to tell me if it's a chemical change or a physical change. That was a big one. Prefixes are another thing. We talked specifically a whole lot. I wanted you to memorize kilo, centi, milli, micro, and how these relate to the base unit: a liter, a meter, or a gram. Base unit for mass, volume, and length or distance. So we're going to work a few problems here in a second on those. But another type of conversion, you'll be given the equations for temperature conversions between Fahrenheit and Celsius, and then vice versa, Celsius to Fahrenheit. Those are on your exam 1 resources page. They'll be on your final exam resources page. So the final exam resources page will kind of be just a compilation of all 4 exam resource pages. So you have those. Just remember how to use those equations. Okay. If I give you a temperature in Fahrenheit, you should be able to calculate it in Celsius or convert it to Kelvin. And remember, you can't go directly from Fahrenheit to Kelvin. You first have to go through Celsius is like the middleman. Anytime you have Kelvin, I'm asked for Fahrenheit, you first have to convert to Celsius. Okay, density is another big one. Density is mass over volume. Units here are grams, volume, milliliters. So if I give you liters or whatever, you could convert to milliliters. If I give you kilograms, convert to grams. But also volume could be conveyed in cubic centimeters. Okay, and remember that relationship between milliliters and cubic centimeters is 1 to 1. 1 cubic centimeter is 1 milliliter. So don't be thrown off if I give you, say you have a cube and it's, 2 cubic centimeters on each side or whatever. You can still calculate density with that. All right, we can use density as a conversion factor between mass and volume as well. So if I said, oh, you've got 5 milliliters of a substance, here's its density, how much would that amount, that volume weigh? What's the mass of it? You could use density to convert between volume and mass or vice versa. Okay, carry out the following conversion. So let's actually do a few practice of these. And again, you may feel very confident with things like this now. These are 1-step conversions. But the way we go about them, remember, so we're doing micrometers to millimeters. I write out the relationship for these things to the base unit. So I know there's 1,000,000 micrometers in 1 meter. And I know there's 1,000 millimeters in 1 meter. So because these both equal a meter, they're equal to each other. So I'm gonna make a conversion factor out of those 2 things. I don't know which way I need to plug it in just yet, but I'm gonna start with 14.4 micrometers. I want to cancel micrometers, so I want it on bottom, and I'm gonna convert to millimeters so that micrometers will cancel. And now I know I just write the associated numbers in. 1,000,000 on the bottom, 1,000 on the top. So 14.4 times 1,000 divided by 1,000,000 should be 0.0144. And now we no longer have micrometers, it's units of millimeters. Okay. So there's one. Let's do another one. Kilograms to centigrams. I'm going to, again, relate both of these to a gram. Okay, so I'm going to say 1 gram equals how many kilograms? I'm going to say 1 gram equals how many centigrams? I know it's 100 centigrams. I know it's 0.001 kilograms in a gram. You could also use this relationship, 1,000 grams in 1 kilogram. You can use that too, but I'm going to relate both to a gram so that I can relate these things to each other and now use this as a conversion factor. I'm going to start with 1.35 kilograms. I want that to cancel, so I'll put it on bottom. I want to convert to centigrams, so I'll write centi on top. So I've got 100 and we got 0.001. So when you do 1.35 times 100 divided by 0.001, you should get 135,000. Okay, and that makes sense to us. A kilogram is really heavy, 1,000 grams. And then a centigram is really small. It's 100 times smaller than a gram. So there should be a huge number of centigrams in a kilogram. Okay. All right, questions on those? Again, maybe you feel good about these. If so, let's actually do one as a word problem. This is 1.76 right out of the textbook. It says a normal value for blood cholesterol is 200 milligrams per deciliter of blood. I think we worked this way back, weeks and weeks and weeks ago, if you remember it. It says a normal human adult has a total blood volume of 5 liters. And how much total cholesterol is present? So pause. Anytime you read a problem, first write out the relationships. What does the problem give you? What units is it relating to what units? And then look at the question. What is your question? Here's my question. How much cholesterol in an adult? So we need to find out what units do we want on our final answer. Okay, so it says normal value for blood cholesterol is 200 milligrams. So it's telling us this is our unit for cholesterol, milligrams. So I want milligrams of cholesterol as my answer. Okay, so I'm going to write my relationships out. It relates 200 milligrams of cholesterol to 1 deciliter of blood. That's one relationship. And it says one adult has 5 liters of blood. And I see I have 2 different units for volume. I've got deciliters and I have liters. So I'm going to have to convert between these two things if I want to cancel volume out at some point and just end up with milligrams. So I need the relationship that there are 10 deciliters in 1 liter. I didn't ask you to memorize anything about deciliters, so I'd give that to you on a problem if it involved deciliters. Okay, so we want milligrams of cholesterol in our final answer on top. So I'm going to start with that, 200 milligrams cholesterol. I'm just going to put it on top, and we know that's related to on bottom 1 deciliter of blood. So I want milligrams to stay, but I don't want deciliters to stay. I want to cancel that out. So how do I cancel that? The only other conversion factor I have that has deciliters in it is right here, 10 deciliters for every 1 liter. And when I write it like this, 1 on top, 1 on bottom, deciliters cancel. Okay, I also want to cancel liters. So I know for every, not 1, for 5 liters of blood per 1 adult. And that's what the question is asking, how many milligrams of cholesterol in an adult body? So it's okay to write per adult, or you could just write milligrams of cholesterol for your final answer. So liters will cancel. So now we do 200 times 10 times 5. You just have ones on the bottom, so you don't have to divide those all in your calculator. 200 times 10 is 2,000, times 5 is 10,000. And milligrams are the only thing that don't cancel. And you could write, again, per adult, or you could just write milligrams of cholesterol. So this is a, possibly a more simple word problem. We've worked harder ones than this. If you want to review these, go back to the lecture slides titled Measurements and download a fresh copy. At the very end, there's some conversion problems that are word problems if you want some challenging ones. Practice those. Here we go. Specific heat will not be on the final exam. Okay, so don't spend time working problems on specific heat. There was a lab at the beginning, conversion lab. It was a dry lab. There's word problems on there if you want to practice more word problems. You could rework those. Somebody asked me this morning, I definitely recommend reworking old exams, reworking quizzes, and any lab content, like look over those things. Any lab content is fair game on the final for sure. So, okay, Dalton's atomic theory. So we're now at chapter 2. All right, so that's kind of the end of chapter 1. Those were the big hitters in chapter 1. Now we're going to look at chapter 2. The first thing we talked about was Dalton's atomic theory. So I'm going to scroll down because I actually have the 4 parts right here. First part said that all matter is made up of atoms. We can't see atoms, but scientists speculated that all things are composed of atoms, and they are. And we have different kinds of atoms. So atoms are different. They differ from atoms of other elements. How so? By their mass. They all weigh different things. They have different masses, and that's represented on the periodic table with their mass numbers and their atomic numbers. Okay, part 3 said that compounds consist of atoms in specific ratios. Okay, only whole atoms can combine into compounds. You can't have a subscript of 0.5. You couldn't have hydrogen 0.5 plus oxygen 1.5. You can't have that. You can only have H2O or H2O2. Okay, so that's what part 3 is saying. Part 4 says chemical reactions only change the way atoms are combined. And they don't change the kind or the type of atom. We can't convert an atom of carbon into an atom of hydrogen. We can't convert an atom of calcium into an atom of potassium. Okay, but we can rearrange them and make new compounds. That's what chemical reactions do. So that's Dalton's atomic theory. I'm going to scroll back up in just a second. We did some true false, or I didn't think we did some multiple choice questions on Dalton's atomic theory back in chapter 2 if you want to review those. After we examined Dalton's atomic theory, we looked at the atom, and we kind of broke the atom apart and looked on the inside of the atom. We looked at subatomic particles. So in an atom, we know we have protons. Those carry a plus charge. Okay. Why are they important? Well, one, we know they weigh something. They weigh 1 AMU, atomic mass unit. And we know they're important for identifying. I'm going to write ID. They identify an atom. Can you go back up for a second to right up here, Key? Or back down to Dalton's atomic theory?
Never mind.
Okay. So we've got protons. They're a positively charged subatomic particle. They weigh 1 AMU, and they identify the atom. We look at how many protons are in an atom. We say, okay, that's how we know it's carbon or whatever. We got neutrons. They have no charge. They weigh 1 AMU as well, same as protons. And they help hold the nucleus together. So I'm going to say hold. It's kind of their role. They also contribute to the mass of an atom. Okay. Varying numbers of neutrons is how we get isotopes. Electrons are negatively charged. They weigh 0 AMUs, and they're responsible for the chemistry of the atom. Okay. That's their role. They determine how atoms behave with other atoms. All right, these two, the protons and the neutrons, are found in the nucleus, and the electrons are found in the electron cloud, which surrounds the nucleus. So if we draw a picture of an atom, we see in the middle where the nucleus is, we got plus charges, that would be protons. We might also have some neutrons packed in there, okay? But then around that is where we have the electron cloud, and this is where electrons are. And we know you can have more than one shell, right? You could have another layer with electrons on that. And the outermost electrons, we have a special name for those. We call them valence. And we'll hit on that more when we get to chapter 3. Okay, so that's subatomic particles and their arrangement. Isotopes was the next big thing. I'm not going to have you calculate the weighted average the way we learned how to do, but I do want you to know something about isotopes. Like I want you to be able to recognize any kind of notation for an isotope and then tell me like how many protons and neutrons. So that's what this problem hits on 2.42. It says give the number of protons, neutrons, and electrons in the following isotope. So I'm going to zoom in on it. So Al27, there's two ways you can write things. You can write the symbol, the chemical symbol. That's the Al part. And then the 27, here we're just given one number. It's the mass number for that isotope, okay? We know the mass number equals protons plus neutrons, right? That's the mass number for the isotope. So we need to look at a periodic table. In fact, if you have a periodic table somewhere, I'm gonna get one. Hold on, you may not see my screen for a second. I gotta get my periodic table up. Where'd it go? I had one on my desktop. So I'm like looking for it. Here it is. Okay, let me get this back in the middle. All right, on the periodic table, I see that aluminum, the atomic number for aluminum is 13. Okay, so that tells me what? The number of protons or neutrons is the atomic number. The atomic number, yeah, is the number of protons. So that means for aluminum, we have 13. So 13 plus what equals 27? So you could just subtract it off. When you do that, you find, so we said there's 13 protons. That means neutrons, when you do that math, there's 14 of those. How many electrons in this isotope of aluminum?
There are 3.
3?
Yes, ma'am.
3 electrons?
Or, sorry, if I'm just counting valence electrons, I guess, but
3 valence. How many electrons total? In a neutral atom, this is not a cation or an anion. The number of electrons. Yep, Haley. Yep, Kennedy.
oh, okay.
Matches the number of protons. That's why the atom's just neutral right now. The positive and the minuses equal each other. So we've got to have 13 electrons. Right now, when we get to cations and anions, it's a different ball game. But in a neutral atom, the electrons and protons match each other. Okay. The second kind of notation you see on B here for silicon, the mass number is the bigger number always. It would never make sense for the atomic number to be bigger than the mass number. Okay, you're not going to have that. So the mass number 28 here equals 14. Just below that, that's the atomic number. Okay, so that is the number of protons. So equals 14 plus the number of neutrons, because the mass number 28 here equals protons plus neutrons. So we see that protons, we're told there's 14. When you subtract off 28 minus 14, we find that there's 14 neutrons, and the number of electrons has to match the number of protons. So there's also 14 electrons. So you just keep going on. Boron, really quick. You're given the mass number there. It's 11. But when you look at the periodic table, I see that the atomic number is 5. So the mass number is 11. The atomic number is 5. So what that means, we know that the mass number 11 equals 5 plus our number of neutrons. The atomic number is the number of protons. So that means we got 5 protons, neutrons. When you subtract that off, we got 6. Electrons has to match protons, so 5 electrons. Silver, same idea here. You just have some bigger numbers. Oh, sorry. We got 115 is going to be equal to protons plus neutrons. Well, this 47 right here, that tells us the number of protons. So we got 47 plus what? Number of neutrons equals 115. So protons, 47 of those, neutrons, 68 of those, electrons, 47 of those as well. Okay, questions so far? All right, last couple of things in chapter 2. We really looked at the periodic table a whole lot. We talked about how it's organized, how it's arranged. We said you've got the rows or the horizontal parts and the family or the groups or the vertical parts. And the vertical portions, the groups, we have two kinds. We have main groups and then we have transition metal groups, okay? And I wanted you to know how to count main groups. You start with the row that has hydrogen. So for example, let me just make this big here. Share my screen over to desktop. Some of you may not have a periodic table right now. Okay, you can see group 1 right here. Main group 1, main group 2. You skip these transition metals. Main group 3, 4, 5, 6, 7, and 8. All right, so this was important because one thing we talked about is that everything in row 1, or sorry, group 1, hydrogen, lithium, sodium, potassium, we said there's similar chemical properties or similar chemical behavior between elements in a group. So if I ask you, tell me an element that would behave similarly to sulfur. Well, you would just go to the group sulfur's in and say, oh, probably oxygen, selenium, I don't even know how to pronounce that, tellurium. You tell me one of those elements, okay? Because they're in the same group. Why do they behave similarly? It all has to do with their valence electrons, which is the next biggest thing, okay? You remember how to count valence electrons across the periodic table? You count main groups. So group 1, main group 1 has 1 valence, main group 2, 2 valence, 3 valence when you skip over here to the group with boron, so on and so forth until you get to main group 8, which has 8 valence electrons. So just a little review on that. Let's go back to the iPad. There's a really good review problem on valence electrons. I'm not actually going to take the time to work it, but it's in the textbook if you want to go check that out. I recommend it. But valence electrons are what? They are the electrons in the outermost energy shell of an atom, okay? And as we examine valence electrons, we said there's something very stable. 8 valence electrons is stable. So everybody's trying to get 8, which is what we call an octet. 8 valence in the outermost shell, that's an octet. And that is stable. So atoms can accomplish that by giving or receiving electrons from their valence shell or receiving them into their valence shell. One more, never mind. So that kind of leads us directly into ions, because when atoms start doing that, they become ions. All right, so now we're in chapter 3. So atoms don't always stay neutral. You have ions, which are atoms with a charge, with an associated charge overall. So what kind of ions do we have? We have cations. Okay. Do these give away or do they receive electrons into their valence shell? Do you remember? Haley said give. Yep. Kiki said So they give electrons away. And what happens is now there's a charge imbalance. The number of protons never changes. So if they have like 10 protons and they start out with 10 electrons, now they give some away. Now they have fewer electrons. So more protons, you see that overall in the charge imbalance. So they have a positive charge when they're done with giving away their electrons. All right, anions are the other kind. If cations give away electrons, then anions receive electrons, and then they carry a negative charge. Because now they have more electrons in the atom than they do protons. So there's an imbalance. And that imbalance is what we write as the charge of the ion. Okay, so this is all leads up to the fact that when you have anion or cations and anions, when you have ions, you can now make compounds that are held together by what we call ionic bonds. All right, so these ionic bonds happen when an electron is completely transferred from one atom to another. and you end up with something that is fully positively charged and something else that's fully negatively charged. And this is unlike covalent bonds where we're sharing electrons, okay? So remember how ionic bonds and covalent bonds are different. And then this follows right into the octet rule. We can actually predict, we can look at any element on the periodic table except transition metals, and we can know, okay, that atom would have this kind of a charge. It would tend to form a cation, or it would tend to form an anion. How do we know that? Well, the octet rule says it is the tendency of atoms to gain or lose electrons to achieve an octet, which is a completely filled shell of valence electrons. That is the octet rule, and it's useful for, right here, predicting charges on cations and anions. So everybody's going to take the shortest route. You look at how many valence they have. If they have less than 4, so 3 valence, 2 valence, 1 valence, it's way easier to give that number away than to gain 5 or 6 or 7 to get the 8. So if they're giving away, those things are going to become cations. So that's what metals do, okay? Metals tend to become cations, and nonmetals tend to become your anions, okay? So on the right side of the periodic table are where you find your anions. On the left side of the periodic table is where you find your cations, plus your transition metals. The very first page of the textbook, if you open up the textbook on the inside cover, it has the periodic table, I believe, painted like yellow and blue and purple. We looked at that when we did this lecture, and that tells you which ones are metals and non-metals and metalloids. Okay. All right, after we discussed the octet rule and ions, then we got into naming. Okay, so we can form all these different awesome kinds of compounds that contain a metal and a non-metal. That's how you know it's an ionic compound also, by the way. It's a combination of a metal and a non-metal, because covalently bonded compounds are usually 2 non-metals. But then we have to name them. If we get all these kinds of compounds, we have to have a systematic way for naming them. So a couple of rules for naming. Number 1, how do you name ions? Well, we have cations that are main group, and then we have cations that are transition metals. And we name them differently. If they're a main group cation, so let me write this out. So if you're a main group cation, you just name the element. Okay, just name the element. That's a calcium ion or a magnesium ion or a hydrogen ion. But if you're transition metal cation, you have to use Roman numerals. You name the element, okay, copper or chromium or whatever, silver or gold or cobalt, but then you use Roman numerals to indicate the charge. We don't do this for main groups because their charge is understood. We know it's always set, like potassium is always a +1 or calcium is always going to be a +2 based on what group they're in. But for transition metals, sometimes they can carry different charges, remember? Sometimes they can give up more than their 2 valence, and they can have a +3 or +4. So we have to use Roman numerals to indicate their charge. But you never use Roman numerals on main groups. So other quick 3 rules. Number 1, cation first. You always, when you're naming the compound, like writing the name of the compound, you always write the cation first, anion second. Rule number 2 is you do not include charges. Okay, so this is for when you're naming compounds, not ions. When you're naming compounds, these rules apply. And then rule 3 is you use parentheses with a subscript when you have a polyatomic and you need more than one polyatomic in your formula to get a balanced formula overall. Everything adds up to 0. So use parentheses for polyatomics when you have more than one. Use parentheses around your polyatomics when you have more than one. So let's practice naming these things. And I actually see a typo on this very first one. This should be a 2, not a 3. Okay. So how do we name this first one? Anybody remember?
Isn't that calcium nitrate?
Uh-huh. Yep. So you just name calcium. No Roman numerals here because it's a main group. So just be calcium. And then look what I have just below. Nitrate, okay? NO3. So calcium nitrate. All right, magnesium phosphate. How would we, we're given the name of the formula here. How would we write, or sorry, we're given the name of the compound. How would we write the formula? It's got to be neutral overall. Anybody remember? So magnesium is main group 2, so it'll be an Mg2 plus phosphate. You can look at your periodic table or your, polyatomic chart. Phosphates right here, PO4 with a -3 charge. So Grayson suggested that it is Mg3 PO42. Okay, and if you're like, how did she know what subscripts? You can always do the switch trick, right? Look at the charge on the cation. That's how many, that's going to be your subscript for your anion. Look at the charge on the anion. That will be your subscript for your cation. So yeah, it should be, when you combine these Mg3, and we have a polyatomic here, and we need more than one. We need 2 phosphates. So it's PO4, and you got a 2 down there. Okay. Now you double check yourself. Does that add up to 0? We've got 3 magnesiums. That's like a +2, +2, +2. So that adds up to +6. Phosphates, we've got 2 of those. So that's like a -3 and a -3. That adds up to -6. So neutral overall. Okay, how about this last one? CuCO3. What do y'all think? CuCO3. How do we name that? What is Cu? Copper. And guess what? It's a transition metal. So we need to decipher what the charge on copper is here. How do you do that? Anytime you have a transition metal, you have to look at what the anion is. So what is your anion? What is the charge on the anion? And how many anions do you have total? Multiply the number of anions by the charge to get the total amount of negative charge. And then break that down, that equals the total amount of positive charge, and break that down by how many cations you have to get the charge on an individual cation. So Kendall says copper here is a +2. So we got CO3, that's carbonate. If you look at the polyatomic chart, that is a -2. And how many carbonates do we have? We just have 1 here. I don't see any parentheses. So that means I know if I split this in half, this side has to add up to +2. How many coppers do I have in my formula? It's an understood subscript of 1. So +2 divided by 1 is just a +2. So I know it's copper when I write this out, COPPER. It's a transition metal, so I'm going to put a Roman numeral of 2, carbonate. Make sense? Okay. Questions there? All right. So you're right, 2 because of copper's charge. You always indicate the charge on your cation with Roman numerals if it's a transition metal cation. Yep. Okay. Chapter 3. So that's it for chapter 2. Chapter 3. So wait, no, sorry, that was all chapter 3. We're still in chapter 3. Sorry. Last question for chapter 3. This is a true false. It won't let me scroll up. It's like not reading my finger. There it goes. Read each of these statements and tell me if they're true or false. And if false, why? So number one, a cation is formed by the addition of one or more electrons to an atom. Somebody was telling me they had anatomy and physiology class and the whole exam is just true, false. Would y'all like a whole exam of just true, false? You're like literally breaking down every word of the phrase, trying to figure out which word is wrong or right. Allie said yes, please. Well, probably not. Okay, cation is formed by the addition of one or more electrons, and I'm seeing here Keegan said false, and he's correct. An anion is formed by the addition of one or more electrons. Okay, next. Group 4A elements tend to lose 4 electrons to yield plus 4 ions. Is that what group 4A elements tend to do? What do y'all think? Liana says true.
Couldn't this be either or? Because they're kind of in that middle spot, or is there another factor that I'm not thinking about?
I think the key word here is tend. What do they tend to do? So if you remember, this has been a while since we talked about chapter 3, so I don't blame you if you don't remember. We said group 4 elements, we don't typically see them in ionic compounds. We find them more in covalently bonded molecules because it's a lot of work to give 4 electrons or receive 4 electrons. It's a huge charge burden on an atom. So they don't tend to do this. They tend to form covalent bonds where they can share electrons. All right. So this one is also false. Because they don't tend to form ionic bonds. It's not impossible, but tend is like saying, what do they usually do? What are most of the time, what do they do? It's not impossible for carbon to have a +4 charge, but it doesn't like to. So that might seem tricky, but that's the key word in this statement. Okay, elements number 3. Elements that form anions are typically found on the left side of the periodic table. So think about that. Left side would be what? Main groups. That'd be like main groups 1 and 2 or main groups 6 and 7. Do they typically form anions? Or do the elements on the left side tend to form cations? Okay, Bradley says it's false. Kendall, false. Yeah, this is false. Okay, why? Anions are that form in finalists. Left side is main groups 1 and 2. Okay, left side, this is main groups 1 and 2. Those tend to form cations, all right? So anions are typically found on the right side of the periodic table, main groups 5, 6, and 7. That's the right side. That's the farthest right. That's closest to the noble gases. All right, any questions on those? All right, so that is now the end of chapter 3. Now we're going to start chapter 4. I think of all the chapters that we cover this semester, chapter 4, chapter 7, and chapter 10 take the most out of everybody. I think they are just the hardest. So let's start with what we began with, covalent bonds. Covalent bonds are formed by the sharing of electrons. So please know for the final, how are ionic bonds and how are covalent bonds different? Okay, covalent bonds are how you get covalent molecules. Covalent molecules are usually formed between molecular compounds between 2 non-metals. And ionic bonds, those are formed up of ions where you have a metal and a non-metal. And we then needed to know how covalent molecules are put together. So how do they form bonds? Well, they share electrons. How do you know how many bonds an atom can form? It all has to do with this little phrase right here, the number of valence electrons needed to gain an octet is equal to the bonds that that element will form in a covalent molecule. So what does that mean? Let's consider nitrogen. Somebody tell me, nitrogen is main group what? Kendall said 5. So what that means, if it's main group 5, you remember how to count valence electrons? They match the main group numbering. So this has 5 valence electrons, right? So how many does it need to get an octet? If it already has 5, it needs 3. So what that means is in a molecule, nitrogen will form 3 bonds. That's why we would always we drew this molecule so many times, especially in chapter 10. You always see nitrogen forming 3 bonds. Excuse me. All right, and that's how it completes the octet. Everybody's still obeying the octet rule here. Everybody wants an octet. Remember, when you share electrons, both atoms in the bond claim both of the shared electrons. So if we zoom in on this bond, there's an electron donated from nitrogen, there's an electron donated from hydrogen. Nitrogen, I'll do this one in blue, nitrogen here claims both of these. It says both of these are mine. Hydrogen says, oh, both of these are also mine, okay? They both claim both of the electrons. So when you count up the octet, you count all the electrons in the bonds around that atom plus any lone pairs, you would see nitrogen has an octet here, 8 around it. Okay. The other thing we talked about, this kind of led right into Lewis structures, because now we're starting to imagine how atoms are arranged and connected together via electron sharing. So we had some rules and we looked at condensed structures. I'm not going to work a problem with condensed structures today, but please practice those. We had a whole lab on Lewis structures. You could rework that or practice it. I believe you could go into any assignment on Mastering Chemistry and rework it, any of the problems there if you want to. Some of you hate Mastering Chemistry, so you will not do that. But there's also textbook problems that you could rework, okay? So let's slide down to the next slide real quick. And I forgot to do this in this morning's review. Don't let me forget to come back to this problem. Naming binary compounds. I didn't even do that this morning. Sorry. Okay, rules and condensed structure. So let's get to the Lewis structure rules. Here are the rules. Number 1, calculate the total number of valence electrons in your molecule. Okay. We'll practice that in a second. Rule 2, you start drawing lines between each atom and connect them. Remember which atoms can be central atoms, which atoms cannot be central atoms. Anything that can only have one bond, hydrogen, halogens, those cannot be central atoms. Anything that can have more than one bond, carbon, nitrogen, oxygen, anything in main groups 4, 5, 6, those could be central atoms. So start connecting them. 3, any remaining electrons. So add up how many electrons you've drawn into your structure via bond so far. See how many you have left. Start putting electrons on exterior atoms, not your central, so that each atom connected to the central atom gets an octet. The exception here is hydrogen. Hydrogen doesn't ever get lone pairs. Place any remaining electrons and lone pairs on the central atom. If the central atom does not yet have an octet after all this, take a lone pair from a neighboring atom, form a multiple bond to the central atom. My favorite example that displays all 5 rules would be CO2. CO2, let's look at CO2. You got carbon, which has 4 valence. Oxygen has 6 valence. Total electrons for 2 oxygens and 1 carbon should be 4 and 6 and 6, 16 valence electrons. So rule number 2 says start connecting things. So you just start connecting them like this. Then rule 3 says start putting octets via lone pairs on all your exterior atoms. So you get something like this. Well, at this point, if you count up all the bonds and the dots, you have 16 electrons in your structure. Uh-oh, my carbon's not satisfied. Carbon has to have 4 bonds. So that's where we get to rule 5. We kind of skip over rule 4 here. We're going to rip off some lone pairs. And we're going to make a multiple bond to the central atom till everybody's satisfied with an octet. Okay. So we're going to do one example because I think you guys remember this fairly well enough. I mean, we were still drawing Lewis structures through chapter 7, at least, and in chapter 8, because we looked at intermolecular forces. Let's just do, which one do I want to do? 1, 2, or 3? Two. So I'll Keegan first. Okay, so we've got how many valence? That's rule number 1. So carbon, I've got 2 of those. Each one has 4 valence. So 8 valence from carbon. Hydrogen, got 5 of those. Each one has 1 valence. So 5 contributed from your hydrogens. Fluorine and oxygen, 7 valence on a fluorine. Sorry, I'm doing my numbers backwards. I just have 1 fluorine in my structure times each fluorine has 7 valence. Just have 1 oxygen in my structure. It's got 6 valence. So when you add all this up, you should get 26 valence electrons. Right, so that's step 1. Now we start connecting everything. Carbon's in the middle. I know oxygen could also be a central atom. So I'm just gonna draw something like that. And then you just start putting your hydrogens and your fluorines can never be central atoms. They can only have 1 bond. So just start putting these. It really does not matter. I could put the fluorine here. I could put the fluorine somewhere else. Just got to have the right number. And then we know oxygen needs 2 lone pairs. Never put lone pairs on a carbon. Please don't do that. So I got 5 hydrogens, a fluorine. I think everything is satisfied. You can count up all the electrons now. Remember, each dash or line that represents a bond is 2 electrons. So 4, 6, 8, 10, 12, 14, 16, 18, 20. What am I missing? I'm missing 6 electrons. See, this is why you follow back up at the end. Yep, Kendall said it. There should be lone pairs. And I might have moved on and forgotten those if I didn't count up in the end. 22, 24, 26. Okay. All right, any questions there? Okay, so that's Lewis structures. There's more examples. You can always practice those. Tons of practice in the book if you need practice with Lewis structures. Let's get on to geometry. That was the next big hitter in chapter 4, looking at molecular geometry and how things take shape and writing the name of the shape for your central atom. So steps here, don't let me forget Autumn, that's right, binary compounds, I'm coming back to those. After geometry. So right here, we're gonna draw the Lewis structure and then you're gonna determine, okay, what atom am I trying to name the geometry of? It's usually the central atom, not an exterior or a perimeter atom. 2, find the number of charge clouds. Remember how to count those? Bonds or lone pairs. You're counting bonds or lone pairs. But the caveat with bonds is that double and triple bonds are just 1 charge cloud. Just because it has 3 bonds doesn't mean it's 3 charge clouds. Bonds, whether double, single, or triple, are just 1 charge cloud. And then lastly, predict the shape. Charge clouds move as far away from each other as possible. Why? Because they're all electrons. They're negatively charged, so they repel each other. And that forces the geometry. So you're going to have this chart. You remember this chart on your final exam resources page. So you'll count up your charge clouds, come here, look at the name it. Let's just do an example. CO2. We already drew the Lewis structure for that a minute ago. All right. You could also think, instead of counting bonds, you could think of counting bonded atoms. Like how many atoms is my carbon here bonded to? I'm trying to name the geometry of carbon. So I'm trying to count charge clouds. So how many atoms is my carbon bonded to? Or you could say how many bonds. If you're counting just bonds, you say, oh, there's 4 bonds here. Okay, but we don't have 4 charge clouds. We just have, remember, a double bond is just 1 charge cloud. Another double bond is just 1 charge cloud. Do I have any lone pairs on my carbon? I have lone pairs on my oxygen, but I'm not naming oxygen. I'm just naming carbon, so I don't have any lone pairs on my carbon. So I don't count the lone pairs on oxygen. So I have 2 charge clouds, and it's all bonded atoms. So scroll back up. 2 bonded atoms, no lone pairs. That is linear, okay? Carbon, by the way, will never be anything that has lone pairs. So it will never be bent and it will never be pyramidal. Okay, and that carbon can never be these. Carbon can only be linear, trigonal planar, or tetrahedral. Let's look at an example where carbon would be the other two maybe. I want to adjust this. I want to say instead of C3H8, let's say H6O. So if you're trying to draw this out real quick, this is the last one we'll do, and then we're going to get to binary compounds. Carbons, 3 carbons here. And we start drawing in the hydrogens, 1, 2, 3, 4, 5, 6. I got an oxygen too, but I have to double bond it to this carbon because I don't have any more hydrogens to put on the oxygen. So let's name the geometry for carbons 1, 2, and 3. Carbons 1, 2, and 3. I see on carbon 1, bonds or bonded atoms. How many other atoms is this first carbon bonded to? 1, 2, 3, 4. So that's 4 charge clouds, no lone pairs. So on this first carbon, we got 4 charged clouds. Okay, so what's the geometry? Well, I'm down here in category 4. That matches this right here, tetrahedral. So this is tetrahedral. All right, what about carbon number 2? There are times when you have to recount different bonds. So you have to go back and recount. I'm also counting this bond for carbon 2 when I'm counting charge clouds. 1, 2, 3, 4. So again, I have 4, no lone pairs, should be same thing. Also tetrahedral. Okay, what about carbon 3? Kendall said trigonal planar. So I've got 1, this is another charge cloud, 2, that's 3 charge clouds. Remember a double bond here, this is just 1 charge cloud. So 2, 3 total for this carbon right here, I got 3 charge clouds, no lone pairs. So this is different. So that we're up here in this category, we said it can never be bent because we don't have lone pairs. So that is trigonal planar. All right. So I think you get the gist of it. Definitely if you feel uncomfortable with this or you're just like, I don't remember it as well, spend some time, practice a few more. Oh, polarity. Don't let me forget, Autumn. Put that in the chat again in like 2 minutes. Polarity and then binary compounds. We got like what? 15 minutes left. We'll finish in plenty of time. Okay, polarity was another big topic in chapter 4. You see why chapter 4 is so like monstrous? All these huge topics. Polarity. So there's polar bonds and polar molecules. First, let's talk about polar bonds. Polar versus nonpolar. How do you know if a bond is polar? How do you know if it's nonpolar? You have to look at what atoms are involved and you have to consider their electronegativity. Okay, so if you have something like this, a hydrogen atom bonded to a hydrogen atom, the nuclei of these atoms are identical, 1 proton. So it'd be like, if you're thinking of tug of war match here, you got these 2 little electrons in the middle, okay? Which way do the electrons want to go? They feel attracted to the positive charge of both hydrogen atoms equally. So this is nonpolar. Okay, but the moment you have something like this, where you got a hydrogen bonded to chlorine, we now have a nucleus, and I'm probably not going to get all the hydrogens written in, but 1 proton versus like 17 on this side. Okay, so it'd be a lot of positive charge that they feel. So I'm going to stop there, but there's probably even more protons. And then you got these 2 electrons sitting in the middle. So which way are they going to be attracted? Obviously towards the chlorine, right? They're going to feel a stronger attraction towards 17 protons than 1. All right, so we call this kind of a bond polar. And we can write in the partial positive and the partial negative. Now, why am I writing a partial negative on chlorine when it has more protons in the nucleus? It looks like there's more positive charge in that nucleus, right? So why am I giving it a partial negative? We're not examining the nuclei directly. Indirectly, we are to see which way the electrons feel pulled. We're looking at which way the electrons are pulled. So we say chlorine here, we got all these lone pairs on chlorine, remember? Plus the electrons in the bond feel tugged towards chlorine, so it's electron dense. Okay, because that's where the electrons are going to be in this molecule. So we say the partial negative is there because that's where the electrons are. So we say hydrogen's electron deficient. So that's why we put the partial positive on hydrogen. So that's just bonds. Okay, what about molecules? Molecules, let's consider something like CH4. You have to look at the individual bonds. Some molecules are very simple like this, where every bond is identical. Every bond here is a carbon-hydrogen single bond. So I'm really only examining one kind of bond. Other molecules are not so simple. Other molecules might be something like this. Maybe you've got carbon-hydrogen bonds, but now you also have this carbon-oxygen double bond. So I got a bond here between carbon and oxygen. Now I have two kinds of bonds I have to examine, a carbon-hydrogen bond and a carbon-oxygen bond. All right, if I look at electronegativity differences, you've got to consider the electronegativity difference. For carbon and hydrogen, it's 2.5 minus 2.1. I'm just grabbing these values off of this chart right here. So it's a difference of 0.4. To be polar, a polar bond, you have to be 0.5 or greater than 0.5. That's a polar bond. So guess what? None of these bonds, this is a nonpolar molecule. Remember, you're considering bonds, you're considering shape, and you're considering the presence of lone pairs when you're trying to determine is a molecule overall polar or not. Okay, so we know carbon-hydrogen bonds are nonpolar. So I know if I'm zooming in on this other molecule, these bonds right here, these are nonpolar. But what about this carbon-oxygen bond? So let's zoom out and calculate the electronegativity difference. Carbon's 2.5, oxygen's 3.5. Okay, so the difference there is 1, and that's greater than 0.5. That's the electronegativity difference. So we do have a polar bond here. And when you have a polar bond that does not cancel via symmetry, drawing a dipole, pointing towards the element with the higher electronegativity. And draw in your partial positive and negative. Sometimes they cancel. Sometimes you can have a molecule full of polar bonds and lone pairs, but symmetry causes all the dipoles to cancel. All right. So problem 4.76 here, and then binary compounds. I'm going to work this. So really quick, I'm going to draw out these molecules. We're just trying to arrange the following molecules in order of increasing polarity. So I'm going to judge the polarity of these bonds and then put them starting with the lowest to the highest. So what's the electronegativity difference for a hydrogen-chlorine bond? Chlorine is 3.0, hydrogen is 2.1 on the chart. So 3.0, 2.1, the difference there is 0.9. Okay, we'll come back to that. pH 3. All I have here are phosphorus hydrogen bonds. So pH 3, phosphorus is 2.1, hydrogen is also 2.1. So guess what? The difference there is just 0. The electronegativity difference. Okay, C, molecule C is water. So draw a molecule of water. I got hydrogen, oxygen, single bonds. So hydrogen 2.1, oxygen is 3.5. The difference is 1.4, okay? So these are the numbers we're gonna evaluate. We've got one more, D is CF4. I know I'm moving fast. Let me know if I need to slow down. And yes, there are lone pairs all over these fluorines, but I'm concerned about the bonds here. Carbon and fluorine. Fluorine has a value of 4.0 on the chart. Carbon is 2.5, so the difference there is 1.5. So I'm looking at these numbers. It's not asking is the molecule polar or not. It's just saying put them in order of increasing bond polarity. So we're going to start with the lowest and go to the highest. So I see that molecule B, pH 3, had the lowest number 0. So it'd be pH 3. That was molecule B. Then it would be what's next lowest is molecule A. That was HCl 0.9. Now between 1.4 and 1.5, obviously 1.4 is lower, so H2O is next. And then lastly, we have CF4 is the highest, increasing bond polarity. Okay. I think this is a great problem. All right, that's bond polarity. In the last few minutes we have, we're gonna look at how to name binary compounds. I think the next slide is, yeah, chapter 5. So we'll pick up there tomorrow at 9 o'clock. Let's go back up. Any questions here? People still writing?
Wait, so for polarity, is like as long as the dipoles aren't canceling, is it that it's if it's 1 or greater, it's polar, or what is it?
So I actually don't have that little table on here, but there's a little table that tells you how to classify things as polar. So an electronegativity difference of 0 to 0.4, this is considered non-polar, Keegan. If something is polar, it's because when you look at all these little values on the chart and you subtract them, you find the difference. The electronegativity difference is 0.5 or greater. I think it's to like 1.9 or something. You'll have this little chart on your resource page. I'm sorry, I actually don't have it on this review. If it's ionic, I think it's because the electronegativity difference is like greater than 1.9. So I look at like K and fluorine. If you had KF and you look at the electronegativity difference there, it's 2.2. That is so different that it's just ionic at that point. Okay. Yes, if you have an electronegativity difference greater than 0.5 or greater, you draw the dipole in. If that dipole doesn't cancel due to symmetry, then that's a polar molecule. All right, I see some yawns, so we're about done. Right. Nope, right here. Okay. Name the following binary compounds. So here's the formula. Use the prefix and then name the element for the first element. Use the prefix, name the element for the second element. Okay. So let's do 2 or 3 of these, and then I'm going to give you a name and have you write the formula. Okay. You always do the less electronegative element first. Less electronegative element first, the more electronegative element second. Okay. And these prefixes are what? We've got prefixes of mono, that's 1, di is 2, 3 is tri. You have a whole table of these on your slides from chapter 3. Tetra, penta, so on and so forth, okay? So what do we have here? Which one looks hard? Just do number 2. Let's do number D. Okay, letter B, letter D, and C, B, C, and D. Should do those. ASCl3, what do y'all think? AS, if you're looking at a periodic table, I have it, it's arsenic. So is it mono, arsenic, prefix, then element name, trichloride? Is that right? Tyler said no, he's correct. Why is that not right? Just arsenic. So that's right. You do use mono, but only in certain cases. Only when you're differentiating between compounds like, and this is a very poor example, I feel like, but basically you always omit mono. And there's only a few cases that you include it when you're differentiating between compounds that are identical, like carbon dioxide or carbon monoxide. So we do not include mono, just arsenic trichloride. And remember the ending of the name For the second element, here is IDE. So that's why we have chloride. Yeah. Okay, C, I don't think you can read it. C is P4S3. So that P is phosphorus. Here we do include the prefix. Otherwise we won't, if we're just reading the name, we wouldn't know there was 4 if we just wrote phosphorus. So it's got to be tetraphosphorus. By just reading arsenic, I know it's mono arsenic. Because if it wasn't mono arsenic, I would have like a di or a tri or a penta something. Okay, but if it's just the name of the element, you know it's just one arsenic there. That's why we didn't include mono. But we got to include tetra here because there's 4 phosphorus atoms. And then we have trisulfide. Trisulfide. What if we had, real quick, let's do an alternate call. What if we had P4S, or sorry, not S, what if we had O3? The reason I want to bring this up is because there's also one other rule that comes into play. It would still be tetra phosphorus. Actually, I want to author this again. Sorry, this is not just, it's not demonstrating the rule I want to display. It was P4O5. Tetraphosphorus still, but it's not penta, okay, oxide. We lose the A. We don't put 2 vowels by each other. It's just pentoxide. Remember, if you have a prefix that ends with a vowel, such as tetra or penta or hexa or hepta, you lose the vowel, drop the A, and write the element name. If your element starts with a vowel and your prefix ends with a vowel. That's not chemistry being picky, that's English being picky. All right, last one, D, and then we're pretty much at time. We would have dialuminum, hexafluoride. That's a U. Here we don't drop the A because our element name doesn't start with a vowel. All right, that's it.